So today our objective is to talk about the ratios of areas. So learn how to use ratios of areas. This comes out of lesson 11.7. And let's see, we have one theorem on here. But most of this is just how to find the ratio of two areas if we're given a certain piece of information about those particular shapes. And so tonight, the challenge is, as you're doing your homework, is to try to figure out the information they give you, what does that translate into the parts that create area? How does that relate to a base? How does that relate to height? So that's going to be the challenge on your homework tonight. All right, so we're going to have multiple scenarios. Now, these are not vocab words. So you are going to ask to find the ratios, or the ratio, of areas of two triangles. Now, in each one of these cases, I'm going to give you different pieces of information, okay? So let's say what I tell you is that you have equal heights. So let me draw two triangles that have equal heights. So we've got triangle ABC. We've got triangle ABD. We've got triangle VDC. Okay. I'm going to drop down a height. And that height is the same for both of those. So what I want to know is what's the area of triangle ABD to the area, that should say triangle, of triangle DBC. Okay. And what we're going to do is for each one of them, we're going to give them their own base. So ABD, we'll call its base little a, and DBC, we'll call its base little b. So when I'm trying to figure out the area of triangle ABD, it's going to be 1/2 the height times its base, which is a. Ratio means to divide. And then it's going to be 1/2, and the height's the same. It just happens to be outside of that triangle DBC. And its base is a little b. So what you should notice is that the halves are the same and they cancel out. The h's are the same and they cancel out. And all that's left is a ratio of the bases. So in words, when you're asked to find the ratio of the areas of two triangles that have equal heights, what you're going to tell me is the ratio of its bases. So the ratio of areas when h is the same try that again. When height is the same, it's going to, well, let's write equals. It's going to be the ratio of the bases. Okay. And again, that's what we proved out there. So when we have equal heights of two triangles, it turns out that everything but their bases cancel out. So all we have to do is figure out what are their bases, put them in the ratio, and we've got our answer. Okay. Let's see, I think I have room to do the next one. What if we have with equal bases? So let me draw a picture of that one. So the big guy is triangle ABC. The little guy is triangle ADC. The big guy has a height of H, and the little guy has a height of K. So if I want to figure out the ratio of the area of triangle ABC to the area of triangle ADC, we're going to have 1/2 the base, and we'll just call the base B in this case, since they're the same. Let's do red. So we'll just call this B from here to here. And the height of the big triangle is going to be the H. And the smaller triangle, it's 1/2 B again, but this time the height is a K. So this reduces down to simply the ratio of the heights. So a summary of that is the ratio of areas when base is the same equals the ratio of the heights. All right, one more scenario. What if triangles are similar? Okay, so let's draw a picture of those. Call this triangle ABC. We've got a height of H and a base of B. And then we've got next triangle. And he's DEF. And its height is K and its base is E. And we're told the triangle ABC is similar to triangle DEF. So, if we want to do the area of triangle ABC and compare it to the area of triangle DEF, we're going to get 1/2 height, or base times height. For the, oops, let me redo that. For the one guy, and then compare it to 1/2, and then the base and height would be EK. So what happens is that the halves cancel out, and you get B over E times H over K. Now, because these triangles are similar, since triangle ABC is similar to triangle DEF, one of the things that comes out of similarity is that all the corresponding sides are in proportion, Matthew. And if that's the case, then that tells us that B over E would be the same as H over K, because the ratios would be the same. Okay? So one base to the other would have the same ratio as one height to the other. So if that's the case, by the way, what would we call B over E or H over K? What are those called? No. I heard her over there. Scale factor. When we have similar triangles, what we can do is figure out a scale factor where we have the ratio of corresponding sides, and we create a fraction and we reduce it to lowest terms. That's a scale factor, and that scale factor holds true for all corresponding sides. So this would be a scale factor, okay? So going back to our original problem, the area of triangle ABC over the area of triangle DEF is going to equal, because the halves go away, B over E times H over K, which could be rewritten as B over E times B over E. We could substitute one ratio for the other. We could have just as easily said H over K times H over K, which means we're going to have the ratio of those corresponding sides would be squared. And since each ratio of corresponding sides is a scale factor, ultimately what we're taking is the scale factor and squaring it. So in words, the ratio of areas of similar triangles is equal to the square of the scale factor. Okay? So these two pieces, or three pieces of information, are what are going to help you try to figure out the ratios of areas. Some of them are easy, some of them are a little harder. So let's go ahead and we're going to do an example. I'm going to do it on the next page so we have tons of room to do it. Is everybody good for me moving? Yeah? Okay. So we have a trapezoid. A, B, C, D. I'm going to tell you some information about that trapezoid. I'm going to tell you that this angle, BAC, and this angle, DCA, they're congruent. I'm going to tell you this point of intersection is called O. I'm going to tell you that this base, the top base is 3, and the bottom base is 5. Okay, so ABCD is a trapezoid. It doesn't say it's isosceles, so we can't assume it. Find the ratio of areas of, and then we're going to go through 3 different scenarios. Scenario 1. I want you to compare the area of triangle COD to the area of triangle AOB. So let's look at COD, and let's look at AOB. Okay, what can you tell me about those two triangles? Dakota?
They have 2 congruent
They what?
angles.
How many?
2.
Okay, so if I have 2 triangles with 2 sets of congruent angles, what can I conclude about those triangles? They were similar. Okay, so I'm going to erase those outlines. So what we can conclude by having the 2 triangles and finding those 2 angles is we can say the angle COD is similar to angle AOB through angle-angle similarity postulate. So we go back to what we just wrote. We said, okay, If that's the case, then if I can find the scale factor of those two triangles, all I need to do is square it, and then I will have the ratio of the heights. So I'm going to take the area of triangle COD over the area of triangle AOB. The only thing I have on them is their base values. So we would have a base for 3 of COD, which would correspond to the base of 5 of the AOB. And because of what we did before, we know that we're going to take that scale factor. So this is your scale factor. And square it. So we would get that the ratio of the areas of those two triangles would be 9 to 25. Okay, let's look at another scenario. What if we wanted to compare the ratio of triangle COD and triangle AOD? So I'm going to highlight those two triangles. Okay, what do you think is going to be true about those two triangles?
They have one side that's congruent.
Okay, yes, but that's not going to help me.
Heights.
They have the same height, right? I could drop down a height that they would have that's the same. Okay? So we have same height. Now, nothing has changed about this problem, right? So basically we've got triangles that are still part of this trapezoid, okay? So what we're going to do is take the bases and we're going to compare them. Now, these two triangles have, okay, let's go back and think about it this way. Because of step 1, where we found out that triangle COD is in proportion to, or is similar to triangle AOB, that means each of the sides of triangle COD are going to have a same sort of relationship to each other, and so are the sides of AOB. Now I put the X there because I don't know the lengths of those sides, but I know that when I compare corresponding sides that the ratio will be 3 to 5. But I don't know exactly what the lengths are. So when I'm looking at that perspective now, and that's going to stay the same, what I'm supposed to do is compare the bases. So the area of triangle COD compared to the area of triangle AOD, because the heights are the same, I'm going to compare the bases. So the base of COD in this particular case would be a 3x, and the base of AOD would be a 5x. So it would give me a 9 to 5. I mean a 3 to 5, excuse me, ratio. Okay. And then the last one wants me to look at triangles OAB and triangle DAB. So let's highlight that one for just a moment. So AOB, or OAB, this triangle, and DAB, what do those triangles have that's the same?
Base.
So they have the same base. So we're supposed to compare their heights. Okay, we're supposed to compare their heights. Okay, so remember everything in these triangles. So for example, if I'm looking at height of this guy, it's going to be a 5x. But when I'm looking at the height of this guy, it's going to be a 3x. Actually, I should probably change his name. And then it also has, because it's incorporating both triangles, so it's going from the top here all the way to bottom here. So it's including the 3x and the 5x together. So what we have for this one when we do areas of triangle OAB to area of triangle DAB, we're going to have height to height, which is going to give us the height of AOB is the small one, so that's the 5x, compared to the height of the DAB, which is from the top of the trapezoid to the bottom of the trapezoid, which is the 5x plus the 3x, which gives us 5x over 8x, which gives us a grand total of 5 to 8. So this is going to be the hardest part, is when you get these combinations.